Kia ora koutou, na mihi nui ki a koutou katoa, ko Glen Rowe toko ingoa. A very warm welcome to you all. My name is Glen Rowe, and it is my pleasure to introduce this live presentation in a series of talks for the 2020 RASNZ online conference. First up, we have Dr. Heloise Stevance of the University of Auckland, who is challenging the reliability of the traditional method of using a single star to estimate the age of star clusters. A new technique is presented, which, when applied to the Matariki cluster, suggests that it could be older than we thought.
All righty, can you hear me? Is it working? You can hear me all right?
Yep.
Yes.
Yep. I'm going to try and show my screen. Show my entire screen. Brilliant. You should be able to see my presentation now. Is it working?
Yes.
Brilliant. Thank you so much for this introduction. Okay, so today we're going to be talking about star clusters and how we define how old they are. Specifically, we're going to be talking about clusters that are close enough to us that we can see the individual components, the individual stars. So resolved stellar populations, not things that are so far away that they're just a big blob on the sky. And even when you've got a cluster that is this close, you still need theoretical models and our understanding of stellar evolution in order to figure out how old it is. And traditionally, as has just been mentioned, we've used single star models in order to do that sort of comparison. That's the standard in the literature. And our group at the University of Auckland is kind of focused on, and not kind of, very much focused on binary evolution. And there's a tool that I started working on last year. I started developing kind of as a side project with my boss, JJ Eldridge, which I called Age Wizard, which is developed in order to address the fact that we only have that single star method is used ubiquitously. But Age Wizard does other things. It also addresses issues that also exist with that single star method, which I'll talk about in a minute. And I'm just going to show you some of the results that we obtained with Age Wizard. Now, one of those results was supposed to be about Matariki, and I will talk about it at the end of the talk. But when I wrote this abstract, I committed the cardinal sin of writing it before we had the results. And so the way I ended it was saying that the Seven Sisters might be older than we previously thought. Now, there is a very good reason why I wrote it that way. And I also have a very good reason for writing this abstract before we had the results, because the data was in the hands of Gleb, my student, mine and Jan's student. So JJ is my boss. She's great. Those are all of the other people that were or are currently at Auckland University. Elizabeth is a very close colleague of JJ. She's in Warwick. And the results we're going to see in this talk today are mostly sorry, I'm losing my words. I work mostly with JJ and Gleb in order to obtain them. So Gleb was working with the Matariki data, and I didn't want to press him too much because he's got exams, he's an honor student. So I wrote it kind of trying to predict the results. But I didn't pull that result out of my hat, okay? I know my science, and there is a reason why I said it that way, because binaries usually make star clusters look younger than single star models, okay? That's just what binary interactions do. Now, binary interactions come in multiple flavors. You've got your mergers, pretty self-explanatory. You've got your mass transfer. So when a star gets too large or comes too close to its companion, its outer envelope gets stripped and accreted onto the companion star. Now, if that mass transfer happens too quickly, so too much matter tries to accrete onto the companion, you end up with a big amount of stellar material just accumulating around both stars, and you get what we call a common envelope. Now, I'll just say that all of these are artist impressions. They're not proper pictures, but they're pretty decent. And the common envelope is a little bit different in real life. It's not as neatly defined as this like figure eight shape. It's more of a big blob around both stars. So what's the effect on our stars? Well, mergers usually equate to rejuvenation. That means making things younger. That's because the material in your stars just mix in the core and everything, and you're starting anew, you're starting afresh. But there's also the fact that when two stars merge together, they make a bigger star. And there is a direct correlation between how massive a star is at birth and how long it will live. So, for example, a 50 solar mass star will have a lifetime of 4 million years, whereas an 8 solar mass star will have a lifetime of 30 million years. And so we can imagine that we would have a situation where a whole bunch of stars are created together around the same time, and we have a binary that after 10 million years merges, and those two stars create a star that is so large that that it just has a lifetime of 3 million years. But the stars around it have an age of 10 million years, and you can't do that. You can't reconcile that with your single star models, right? This big boy should have died already, but it's just come from a merger. So you have this kind of picture that becomes much more complicated when you include binary interactions. Mass transfer also helps make things more complicated, because when you have mass transfer, you end up with stars that have stripped envelopes. Stripped envelopes can happen in the single star paradigm, but you need your stars to be very massive. The more massive the star at birth, the more luminous. There is a direct relationship that evolves very quickly with luminosity. And the more luminous a star is, the stronger the stellar wind. And if you've got very strong stellar winds, your star can strip itself, basically. But that only happens in very rare cases at the very far end of the mass distribution. You need to have the most massive stars in the universe for that to happen. But with mass transfer, you don't care how massive you are. You just need your star to be close enough to its companion, and then you've got stripped stars. So much lower mass stars can end up being stripped. The reason that's important is, like we said earlier, lower mass stars live longer lives, and stripped stars are hotter than their non-stripped counterparts. That's pretty self-explanatory. If the outer layers of the star is gone, you're closer to the core, you're hotter. But in the single star paradigm, again, there is a direct relation between how hot a star is and how massive it is at birth. And on the main sequence, the more massive a star is at birth, the more luminous and the hotter it is. There is a direct relationship, again, between luminosity and temperature. So that's pretty simple in the single star paradigm, but in the binary case, you've got, that mass transfer stuff happening and there's mergers. And so the picture gets pretty messy. So here we've got an example of how complicated it can get. We've got HR diagrams. So I'll explain briefly what the HR diagram is. We're going to see a few in this talk. The HR diagram is a plot where you have temperature on the x-axis, and note that the large temperatures, the high temperatures are on the left, not the right. It's inverted. And we've got luminosity on the y-axis. And it's a very useful tool when looking at stellar evolution in general. So you can plot your stars on this diagram. Here we have an actual cluster. Someone's not muted. Can we make sure that everyone's muted? I can hear ruffling of papers and stuff. So here we can see a cluster, USCO, it's not very important. In the background, that gray heat map that you can see is BPAS, which I'll introduce in a minute. It's my boss's simulations, a mini universe in a computer that can simulate both single star and binary star models. The darker the location on the HR diagram, the more likely it is that you will find a star here. And this diagonal thing is the main sequence. That's where stars live their lives for 90% of their lives. That's the top of the main sequence. And then when a star reaches the end of its life, in the last 10%, it kind of goes off of it. It does something funky. In the single star model, It's pretty simple. It goes off to the right, and you get the red giant branch, etc., etc. The binary model gets much more complicated. Even the main sequence is a lot wider in the binary model because you've got all of these interactions that can occur. So if you're looking just at single stars, you could pretty much draw a line through this and use that as your model, and people do. But the long story short is that binaries make stars look much younger. And we can see this very clearly in this plot. For example, if you were looking at a cluster and you saw a star in this location, you could explain it with the binary model because, you know, we've got a pretty dark shade here, but it doesn't happen in the single star model. In order for a star to exist in this particular location, you'd need the stars that are either dead or dying in this region to veer off to the left and go back to that position on the main sequence. So that's why you can seriously underestimate the ages of your clusters if you only consider single stars. So binary stars make your clusters look younger. Now, isochrone fitting is the line I was talking about. If you just draw a line and you use it as your single star evolution model, that's called an isochrone. Iso means same, chrone, chronos means time, same time. It's the line of that stars follow when they have all the same age. Okay. And you can plot it and try to fit it to your data. Now, the problem with this method is not just that it doesn't have any binaries, although it is a big problem because binaries are ubiquitous. They're everywhere, especially at the high mass end. So stars that are more massive than 8 solar masses at birth, 70% of them will have binary interactions in their lifetime, and that has a strong influence on their lives. But the problem with isochrone fitting doesn't stop there. It's often done by eye, so not particularly rigorous, and there's no great measure of uncertainty. And that's something that I'm particularly obsessed about as a scientist. Having an idea of how uncertain I am about a measurement or an answer that I find is very important to me. And that's where AgeWizard comes in. So it compares observations of resolved stellar populations to BPAS to infer the most likely age. It does not just give you one age, it gives you a whole distribution. It gives you probabilities, which is pretty important. So BPAS, since I've mentioned it a couple of times, let me just quickly introduce it. It's the Binary Population and Spectral Synthesis Code. That was written by J.J. Eldridge and Elizabeth Stanway, who I mentioned earlier on. It's been a staple of binary evolution for over 10 years now. And the idea is pretty simple. You create a population of that contains 1 million solar masses, and then you distribute that amongst stars according to 9 different initial mass functions. If you don't know what an IMF is, you don't need to know. It basically tells you how many massive stars and how many low mass stars there are. It also takes into account 13 different metallicities. That's how much of the elements heavier than hydrogen and helium there are in that simulated universe. And what's very important, what I find really, really good about this code is that the periods and the mass ratios of the binaries and the proportion of binaries are taken from observations, from actual surveys that have been done. So it's a realistic sample. It represents the universe as we understand it today. So once you've created that population, you evolve it, you make it grow old. There's 51 time bins in BPAS that range from 1 million years to 100 billion years, so much older than the age of the universe. And it includes binary interactions, rejuvenation, mixing, stripping, common envelope evolution, all of that good stuff. And on top of that, we're not going to talk about this today, but I'll just mention it because it's in the name. It does spectral synthesis. So it takes those stellar models and it calculates spectra based on other codes, and it can give you a spectrum for your whole population. But other than the spectrum, it also gives you a host of data. So many different stellar parameters. For each stellar model, there's about 250,000 stellar models. Each of them have hundreds of parameters that are calculated for all of the time bins. And because there is so much data, I've created a library in Python called Hoki. If anyone is interested in using BPAS, this is kind of your door of entry if you don't have the expertise to do some of the data preparation, and that can be very, very difficult, especially for color magnitude diagrams. Anyways, AgeWizard is only one part of Hoki, but it's kind of taking in a life of its own with all of the development that we've done around it. But it's part of that ecosystem of making BPAS accessible. So how does AgeWizard work? I've talked about it, but now I need to actually tell you what the algorithm does. Okay, so if we imagine an HR diagram in BPAS, like a simulated one, so that would be our temperature axis here, that would be our luminosity axis here, and we'll talk about color magnitude diagrams a little bit later on. Just FYI, that's just a proxy for an HR diagram. It's slightly different units, but it's a proxy, so it's the same idea. So anyway, in our simulations, what we get is a grid, basically, and all of the cells in this grid have a number associated with them. And the higher the number, the higher the proportion of our simulated universe falls in that square, and the more likely it is that you would observe a star in that location of the HR diagram. And here I've drawn a very bad pixelated main sequence and then a red giant branch going off. So what we can do is take our observation, put it on that grid, and figure out what cell it falls on. So it would be this one in this case. And then when we've done that, we can have a look at all of the time bins in BPAS and see how the number in that square evolves over time. And when we record that and normalize it, we get a probability distribution function of the age. Okay, it tells us what's the probability that this star or this location in the HR diagram has a particular age. So we've done that for the first sample that we used as a test was NGC 300, or rather 2 H2 regions in AGC 300. H2 regions, FYI, it's just it's kind of like Orion is an H2 region. It's a region of space with very, very young stars, loads of gas, loads of ionized gas, lots of exciting, pretty colors. But very young stars is the main point of it. And as we'll see, it can be difficult to age very young stars with isochrones. So in that case, we've got 16 stars. Those are the individual probability distribution functions that we can see here. And we can combine them all together to get a PDF for the whole region. Ignore the 3 different colors. They're just the 3 different metallicities. We don't need to talk about it today. But you can see it doesn't just give you the best age, which you'd get with an isochrone. It gives you the probability of each age, and you can see how certain or how uncertain your model is that this particular observed region fits a particular age. And to compare it to isochrones, I've made this figure for the paper. This, by the way, this whole data set and this whole paper came out back in August, something like that. So that's already published and refereed and everything. So we've got isochrones here, so state-of-the-art isochrones between log age of 6.5 and 7. And we've got our data set. And as you can see, because we don't have any red giants or anything on the red giant branch, it's very hard to tell which one you would pick or how you would fit that. There's no way to tell. If you picked the most luminous star as your kind of determinant, then you would pick an age that is 0.2 dex, so that's just 0.2 units in log space, different between the isochrones and AgeWizard, and the best fit for binaries. So with this lower sample size and this low an age, isochrones are not very reliable, but AgeWizard does a pretty good job. And this kind of brings us to Matariki. So Matariki is one of the clusters that we are looking at now because we are further developing AgeWizard. So NGC 300 and that stuff was kind of the proof of concept. That's where we developed the first algorithms for AgeWizard. Now we're trying to make sure that it works across the board. and that is systematically reliable. Because one of the things about Isochrone, so this is the best fitting isochrone for Matariki, one of the things about isochrones is that they're very easy to use, because people can just do it by eye and just plot it and see if it works. It makes it very convenient. So if on a practical level, it doesn't matter how good our method is, if the isochrone does an okay job and it's super easy to use, people will just use that. So if we want to use develop a method, it has to be just as easy for astronomers to implement. And by easy, I mean they don't have to think about it too much. So there can't be too many caveats. And Matariki was a caveat. So that's where we encountered not problems, but something that we should have expected, and that kind of caught us by surprise. It was the effect of the lower main sequence. So the main sequence, it's this beautiful S shape. So when I was telling you that we were just looking at the top of the main sequence earlier, we're looking at a square kind of like this, but the full main sequence looks more like this. And the main sequence is also a mass sequence. So like we mentioned earlier, the lower the mass of a star at birth, the less luminous it is and the less hot it is. That's where it falls on the main sequence. And as we said, the lower mass stars have much longer lives. So a star that's born in this location will stay there for a very, very, very long time. And so what that means for the H-wizard method is that if you look at the value in that square over time, it doesn't change that much. And so that distribution is going to be very broad and is going to be dragged towards lower ages. And so if you have a very large sample that includes loads and loads of stars in the main sequence like that, you get different answers if you include different parts of your sample. So if you just look at the top of the main sequence with stars that evolve very quickly, you have a PDF that's very narrow and very young. And that's actually a little bit younger than the best fit with the isochrone. If you include more of the main sequence, you get a broader and older PDF, and more as you include more and more stars in the lower main sequence. That's perfectly expected and in line with what we know about stellar evolution. And it's not really a problem. It just means that we need to make H-wizard more clever. And it's part of the work that I'm doing now. It's figuring out a way to make this part of the HR diagram and color magnitude diagrams matter more. Because if we were to fit it by eye, we would make it matter more because we know it does. This part of the HR diagram I've not talked about much yet because it's not there in NGC 300 and it's not there in the Matariki sample. So the red giant branch is super important for aging as well, because remember when I said that stars spend 90% of their lives on the main sequence? It means they spend only 10% of their lives doing that sort of trajectory. So they do it very quickly. So if you find a star in this location, that square is not going to be populated for very long compared to the main sequence. And so it will give you an aged PDF that is much narrower, that is much more certain and much more focused on the actual age of your cluster. And we see that with other clusters in our larger sample that Gleb is currently working on. So that's nearly it for me. So the long story short, as far as how old Matariki is it is indeed about 100 million years. It fits the binary models and the single star models both agree. It's not necessarily a surprise. Isochrones aren't always wrong, bless them. And as far as H-wizard and the development is concerned, well, we're going to be accounting for the lower main sequence in a new release in the next few months. That's kind of our next objective. I think it might even be a student project. We've got a pretty good idea of I've got a pretty good idea of the theory behind it. Like I've explained, the top of the main sequence matters more. Now it's a matter of what's the maths that we're going to put on it, okay? What's the maths we're going to put on it? Because the way we can do it is by giving a weight to these stars. When we combine the PDFs, to make the PDFs of the full cluster, we can just give a factor to the more luminous stars and make them more important than the less luminous stars. But the question is, what is that factor? How does it evolve with luminosity? What makes sense physically, and what is more likely to give you good results across the board systematically? That's the point. And finally, another very important thing that I want to do, that I'm actually currently working on, is taking into account observational errors, because the breadth of that PDF just tells us how naturally uncertain the age is because of the nature of stellar evolution and stellar evolution theory, which is a very important measure to have. But each and every one of these points also has error bars, because observations are not perfect. And we also need to take into account observational errors in our final probability distribution function to have an uncertainty that reflects not just the things we don't know in our models or the things that can't be known from the models, but the things that can't be known from observations, because we're limited by the width of the error bars. So yeah, that's pretty much it for Age Wizard. I'll be happy to take any questions now, either from the YouTube chat or from the people of the group.
Okay, thanks very much, Heloise. Yes, it's something I omitted to mention in the introduction, that if anybody did have questions, to please use the chat function, and we can have a look at those and put them to our speaker. So I don't know whether anybody
Yep, we have one
got
question
in earlier.
from John Drummond so far, who wants to know, is it still the general consensus that nebulosity around Matariki isn't associated with it?
I don't know. I don't know exactly what that refers to. It depends on how distant it is to the stars in Matariki. So Matariki is too old to be an H2 region that has nebulosity that's directly associated with the very young stars in its cluster. It's about 10 times too old for that. H2 regions have a maximum age of around 10 million years, maybe 12, 15 if you push it. And at 100 million years, there's no longer those very, very young stars that strongly ionize gas around them. So if there is nebulosity, I don't know what it would where it would come from.
Thanks, Heloise. We haven't got any more questions on the chat right now. If anybody's got any, get them in quickly.
Well, if there's none straight away and Heloise is prepared to stick around, we can ask them at the end of the next talk. How's that sound, Heloise?
Yeah, I'll check the chat and see if it's it's caught up, I think. Awesome. Okay.
All right. Well, we'll move on to the second talk of this session. So now we have Steve Butler, the RASNZ President and Convenor of the Dark Skies Group, who will describe how satellite-based measurements of light spill can be used to monitor the impact of outdoor lighting, and asks, how can we make use of this information? Over to you, Steve.
Kia ora tātou. Good evening, everybody. I'm not sure if we've got my screen up as yet. There we go.
Yes.
Does that look all right from your end?
Yes.
Yes, we can see it.
Okay, I'd like to just take a moment to thank Glenn, Warwick, and the rest of the Standing Conference Committee for providing this opportunity for us this year. It's been a rather remarkable year in many ways. the Standing Conference Committee have had to show quite a bit of flexibility and some quite strong decision making, but fortunately they've been able to get us to this point. Also, I'd like to thank Steve Henley for providing the technical support for our talks. Okay, so my talk really is just trying to make use of the information that is starting to develop. We've often had measurements of light pollution being quite sporadic and quite localised, ground-based measurements, earlier satellite measurements, which were useful but not, it still only sort of showed a snapshot in time. So we're now starting to get a bit of a broader base of information that we can start to use. So as an introduction, as my abstract was, with any environmental issue, we need to know how much of the issue there is, whether it's changing, whether it's static. And with satellite-based measurements of light spill into space, we can start to see some of those changes across timescales and across technology or development changes on the ground. And so the question is, how can we make use of this, certainly within RASNZ? Just a bit of a brief summary. We've sort of take day and night a little bit for granted. During the daytime, obviously the sun shines on us. Sun's a broad spectrum light source. As the sunlight enters through our atmosphere, the blue light scatters a lot in the atmosphere and turns our sky blue. The blue light portion of that spectrum scatters at about 4 times greater rate than the red end of the spectrum. So it's quite significant and quite a dominant feature of our life on this planet. Towards either at the start of the day or at the end of the day, that same sunlight is travelling through more of our atmosphere, and so the shorter wavelength light, the blue and the green end of the spectrum, is filtered even more, and so the remaining light that reaches us on Earth in the sunset sunrise period is significantly redder than otherwise. So that's a little bit of a summary of the reality. To give an assessment of colour temperatures of light, this little chart just gives us a bit of an overview of a measurement range based on degrees Kelvin, and it's while it's called common colour temperatures here, the more correct term used by the lighting industry is correlated colour temperatures. So a blue sky in the middle of the day and typically looking away from the sun, so if in the southern hemisphere, if you turn around and look upwards towards the south, you would get colour temperatures of around 10 to 20,000 degrees Kelvin. An overcast sky drops dramatically down to about 6,000 or 7,000 Kelvin. And sunlight, direct sunlight at noon, with that filtering effect of the atmosphere, the direct sunlight's around 5,000 to 5,400 Kelvin. If you slide further down, we start to get into some of the lighting technologies that we've had over the years. Fluorescent lights, 4,200 Kelvin. Sodium vapor lamps further down at 2,200 Kelvin. And so that particular one there represents the older lighting, street lighting technologies in New Zealand, the high pressure sodiums, and down to that sunset sunrise time of about 2,000 Kelvin. So you can see it's getting quite red. If we look at artificial lighting sources, there's an indication of the say a 5,000 degree Kelvin LED lamp perhaps has got quite a bluish white tinge, very blue rich white light source. 4000 Kelvin has less of that blue, 3000 Kelvin is slightly warmer colour again, and then 2700 on the right is quite a warm light source. Still not down to the sort of yellow-orange colours of the high-pressure sodium lamps, but it's trending down that way. So the original LEDs that were first produced were probably up about 6,500 Kelvin. So very cold, harsh, blue-rich light source. So if we look at the spectrum of these particular light sources, so the first one showing is the sort of recommended street lights spectrum for New Zealand street lights, 4,100 Kelvin, and you can see that it's a reasonably broad light source and quite a strong blue band within it. 3,000 Kelvin is a lighting or correlated colour temperature that is allowable in New Zealand for dark sky protected areas. We are not of the same opinion. We think that's still too blue rich, too broad a spectrum, even for dark sky areas. It actually relates to the maximum allowable by the International Dark Sky Association. Here's the high pressure sodium that we're moving away from, and you can see that it's very sort of yellow, red, rich, almost no blue in it at all. So that's sort of what our standard lighting is at the moment, or previously before the LED changeovers. And a low pressure sodium light source, which is favoured by astronomical observatories, relatively easily filtered out of observations, and that would come in at about 1800 Kelvin, degrees Kelvin, almost the equivalent of a candle burning. So though the low pressure sodiums are no longer being manufactured worldwide. So in terms of New Zealand guidance, just a summary, New Zealand Transport Agency recommend 4,000 Kelvin, but will allow 3,000 degrees Kelvin. Mackenzie District, that's the dark sky reserve at Araki Mackenzie, is Mackenzie District Council of approval for installing 2,200 Kelvin. So that was quite a breakthrough. The Australian New Zealand standards provide an upper limit of 4,000 degrees Kelvin as opposed to the recommended level for NZTA. And there's the Dark Sky Associations. They will only allow a maximum of 3,000 Kelvin in the dark sky area, and they prefer way down at 2,000 Kelvin for ecological protection. That's this comparison chart here has got three light sources on it. The very broad dark line curve is the 4,000 degree Kelvin. That's pretty much equivalent to the New Zealand street lighting preference. So this graph is showing the relative spectral power distribution at each wavelength of the light. So blue is at the left-hand side of that scale across the bottom, tending across to the red end of the spectrum at the right at about 700 nanometers. So at 450 nanometers, we can see there's a very strong spike in power, spectral power coming from this light source. That correlates with blue on the spectrum. So we have a very strong blue peak, drops away again, and then comes back up through the orange, or sort of green, yellow, orange into the red. The reddish curve on this chart is a 2200 Kelvin white light, and that's sort of the equivalent of what's being installed in the Mackenzie district. So they've, by changing the coatings on the LEDs, they've been able to suppress the blue peak in the light and shifted the whole light spectrum across to the redder end of the spectrum. So that's much more preferable for a dark sky area when you consider that the blue scatters so readily in the atmosphere. The pale or the blue line through there is moonlight. So it's doesn't have that blue peak. It's broadly spaced around the green, yellow, orange, red part of the spectrum. But one of the anomalies or one of the weaknesses of the correlated colour temperature, what would you say, classification, is that the 4000 Kelvin LED and the moonlight share the same correlated colour temperature. So they're both roughly 4000 degrees Kelvin. And that just indicates that correlated colour temperature classification is not robust. So you've got to be very careful and look at the spectral distribution of the light source as well. But that similarity between moonlight and 4000 Kelvin played a part in the choice of 4000 Kelvin for street lighting. But unfortunately, it wasn't a valid comparison. It has proven to be quite a problem for us. And here's just a great photo that shows the issue with blue rich lighting. This is a wonderful photo from the top of the Remarkables looking down onto Queenstown. Got Frankton at the right hand sort of side under the blue glow. That's Frankton Airport. There's the dark patch in the middle. You've got Frankton Arm roading network through the middle towards Queenstown on the left-hand side, which is under a whitish glow. So the blue glow at the right-hand side, Frankton, is it's a very rapidly growing commercial area. A lot of blue-rich LED lighting for car parks, supermarkets, shopping centres, that sort of thing. The orangey sort of road along Frankton Arm is probably the older style sodium-based street lighting. The white glow at Queenstown will be a mixture of metal halides and some LEDs, but sort of a mixture of lighting technologies. So it's just a great example of the impact that the blue-rich LEDs have on sky glow above an urban area. Hardly any sky glow above the sodium lamps, and a moderate amount of sky glow above the older mixed technology lights towards the left. The Ministry for Environment a couple of years ago have started to acknowledge that light pollution is something that needs to be considered, and so this is now part of the environmental reporting series for New Zealand. There's a couple of about 5 pages in this document related to light pollution. And in here they're saying there's increasing awareness of the importance of night skies for tikanga Maori cultural practices, unique science and scientific values, and the health of native species and ecosystems. And I suspect human health must come under native species and ecosystems, so steer clear of that at the moment. But right down at the bottom it says it's estimated that over half of New Zealanders are unable to see the Milky Way. And that's from urban areas, obviously. So Statistics New Zealand also have a website, a web page related to light pollution, and this is a chart from their site. So that's an image of New Zealand at night showing light pollution from there. Now, the information that Ministry for Environment and Statistics New Zealand are using comes from this satellite here, which down on the right-hand side, bottom right, is the Visible Infrared Imaging Radiometer Suite, or VIRS, as it's otherwise known. This is a polar orbiting satellite which is scanning the surface of the planet for a variety of uses, but is useful for picking up nighttime lighting on the surface of the Earth. And from that, the information gleaned from that satellite information has been made available on this website, Light Pollution and mapinfo.info. Well worth having an explore in there. Information from that is available for pretty much every urban area on the planet. And here's Invercargill, my home patch. There's two pieces of information there that I want you to take a note of. There's a 4-kilometre radius circle over the top of Invercargill, and the minimum and maximum numbers mentioned in the wee box just above it is visual magnitudes per square arc second. So these two red dotted lines across the bottom of this chart are represent those two figures, and it just sort of shows the maximum darkness within Invercargill is not too bad, just below 21 magnitudes per square arc second in the second column. From the left, if you go right across to the right, and it's a bit obscured on my screen, but it's probably around the 5,000 stars visible, down from a maximum of about 6,000. And so the minimum darkness, or the minimum amount of darkness of the sky is the other figure at about 19.8 visible magnitudes per square arc second, and we've immediately dropped to about 1,500 stars available in the sky. So that just gives, that previous information from lightpollution.info is still a single shot in time estimate of how bright an area might or might not be. As it happens, the Royal Astronomical Society of New Zealand have a number of affiliated societies spread right across New Zealand. There's quite a few in the North Island, 16 I think, 5 in the South Island at the moment. So what we're starting to look at is a second website dealing with the same information from the various satellite light trends .lightpollutionmap.info, and again this is a chart of Invercargill. There's a little toolbox on the upper left hand side of the screenshot there with the red polygon. So you just quickly hand draw a polygon across the top of Invercargill. A toolbox or an option box opens up, and at the bottom of that is a generate chart option. So quite easy to do, and that chart then gives us summed radiance of Invercargill, and from 2012 through to the current time. And so it's showing a trend line, and it's quite nicely sloping downwards. The figures are radiance is 10 to the minus 9 watts per square centimetre squared steradium. And that's really just sort of measuring on a curved surface as the satellite travels over the surface of the Earth. So it's scanning. These are summed monthly figures of light coming up into space from Invercargill. So, thinking of all our affiliated societies, I've charted for each of these of their home areas, and as you can see, there's a real mixture of downward trends, some upward trends. I'm thinking that Hibiscus Coast down the bottom right is probably as a result of expansion, development of urban areas, rapid growth out that way, I suspect. Further areas, some quite Napier Hastings. We'd certainly like to investigate what's going on in that area. Hawa has got a nice downward trend. Hamilton's fairly constant. So, we can start to get some fairly interesting information with a time-based trend. More Auckland slight upward trend, Nelson, Richmond also slightly upward, and again some more of the options. We're just going to have a closer look at a couple of these. There's Wellington. You'll notice the y-axis on the left is pretty high radiance levels for a large city, and so the measurements are quite tightly grouped around the trend lines. They're quite constant radiance figures. And Whakatane, the y-axis values are quite a lot lower, so there's less light coming off that area. It's got quite a nice downward trend. So well done, Whakatane. If that's real information, that's good. So I just want to go back because there's a little bit of an issue that I noticed when I was looking at some of these charts, and particularly our local Invercargill chart. And you'll look towards the right-hand end of the trend line and start to look at the monthly readings, and you'll notice there's quite a drop-off. So there's potentially change going on in the background. Whether this is real change or not, we'll see. So what I've done, if I just go back, that's the full trend from 2012 to 2020. I've broken that down to 2012 through to 2018, and it's a pretty solid upward trend in light or radiance off Invercargill. But if we look at from 2017 to 2020, there's a very strong downward trend. So we need to, that my first reaction is that coincides with the start of the transition from old sodium lamps to LED lamps. Part of it is shielding, and that's what my first impression was, that we're getting a lot less light spill. But there's an issue, and that is that the VERS radiometer suite is almost completely insensitive to the strong blue light emissions of white light LED products. So just to expand on that, there is a real limitation in the data coming down from the satellite, and it's that the spectral, the VERS device is measuring light in the spectral range of about 500 to 900 nanometers, whereas human vision is 400 to about 700 nanometers. So the satellite data is therefore less sensitive to white light than the human eye. And so for this reason, when communities switch from orange high-pressure sodium lamps to white LEDs, the satellites often report a drop in brightness, even if a human would say that white LEDs look brighter. So since most cities in the world are changing over to white LEDs, it's very important to keep this in mind. And here's just a diagram. The upper half of the diagram shows the sort of light spectrum or spread of the high pressure sodium, not much blue or green light within the spectrum, mostly yellow through to red end of the spectrum. So it would be a warm orangey coloured light coming from that lamp. An LED lamp at the bottom, strong blue peak in the spectrum, strong in the green, yellow through to the reds. And then the dotted lines over the top of that is the sort of sensitivity range of the various instruments. So for an LED lamp, it's just not, for LED lighting, it's just not seeing that strong blue peak below 500 nanometers. So quite an issue, and that is probably the explanation for those drop-offs in the graphs, the trend lines. So this is what I was considering, and my first reaction was on the left we have the old Cobra head street lights with a big drop lens underneath which scatters light everywhere. Often those lamps in New Zealand are tilted at 15 to 30 degrees up above horizontal, so there's even more spill light coming from them. The one on the right is a fairly standard Cobra head LED style lamp, and it's huge, typically mounted fairly flat and pointed. The light trends almost vertically downwards, so there's very little spill up into space. Any very little direct spill up into space. So the way forward, because we've got a lovely group of affiliated societies spread right across the country, what I would want societies to perhaps consider is that they should add their own trend data to their society's website. Start a conversation with local government, your local city council or district council, and acknowledge the weaknesses in the measurements, but monitor trend over time and update that information as time goes by. Link the changes that you see in the trend data to positive or negative changes to lighting or other changes. So it could be that your town is just starting out on the change to LEDs, or there could be new suburbs being built, or new shopping centres, new sports fields, whatever. If you can start to link changes on the graph to changes on the ground. Support changes if they're being made, particularly the positive ones, obviously. Challenge the decision makers, make them think about the choices that they're making. Link it back to the Ministry for Environment's reporting, link it back to your website, and highlight issues with the media. So if you've got a really strong upward trend, have a talk to your local news people. So there's a wee challenge for us all. Be interesting to see what will develop from that sort of work. Thank you.
Okay, thanks very much, Steve. Yeah, an interesting analysis of those, the information on that light pollution map info, and a warning, I guess, to always look a little bit deeper than the information might be indicating at first glance. So, do we have any questions in the chat there, Steve?
There aren't any questions. There was a question from John Drummond who wanted to know what the website address was, but I've posted that in chat because he wanted to know where can the societies find the city light trends. But what I am interested in is, obviously, Steve, you've done a little bit of work and produced those, and you mentioned it would be great for the societies to put it on their webpage. I wonder if you could maybe make those available the ones that you've already produced, if it's a little bit easier for some people. What I can tell you on behalf of Auckland Astronomical Society, I think that's a great idea to put those light trends on the website, and I'll be making sure that Auckland Astronomical Society has got that on there within the next 24 hours, because I think it's a great idea.
Brilliant, thank you. Yeah, I'm happy to to share that those charts. I would encourage people to learn to do them for themselves, and I'm very happy to help with that process. I think there's other information that you can probably have a look at. You can play around with some of the settings, and I think that it's a treasure trove of information.
Thanks, Steve. I'll certainly be having a look through there, and I'll be interested to look at different regions and as you say, try and correlate if we know there's been any changes in technology, what that looks like in the graphs.
Sure.
No other questions on the chat at the minute. If anybody's got any questions for either Steve or Heloise, who's still around, then get them in quickly. John Drummond has just said one issue I'm finding these days are security lights. So have you got any comments about security lights, Steve? Yeah, certainly security lights should only be lighting the property that they're designed for. They should only really be on if they need to be on. Security lights don't work at all if there is nobody around to report movement or motion. If somebody's breaking into a industrial yard or a car park or something, if the neighbours are all got their curtains pulled, or if there's nobody around, it doesn't really matter that the security lighting is on. The better approach is to use motion sensors, in particular, to only come on, only turn the lights on if somebody is in the area. That then creates a change which people will notice and hopefully report. There's a growing trend to use video surveillance with infrared or lighting, which is much less disruptive. That technology's improved quite a lot. Yeah. Thank you. Yeah.
Okay, I've got one. If I can, grab the floor, Steve. So the y-axis of those various plots from the cities where there's affiliated societies,
Yes.
there seemed to be a variation in the scatter in the y-axis. Was that just because of different scales in the y, or is there really different variations in the different cities, or can you explain what we're seeing there?
I'm not sure that there's I think the distribution or the variance is in the y-axis rather than the x-axis. So I'm finding that in the larger urban areas, the distribution around the trend line is a lot tighter. So, are you seeing my screen at all?
Yes, we are.
Yep. So, what's showing there? So Dunedin and Christchurch are reasonably compact. Gisborne's reasonably compact, but then you get into some of the smaller areas. Where are we? No, Whakatane's pretty compact. I thought there was Hawera. I'm looking for Hawera. Levin's quite a small area, and so the variation is actually quite, there's a lot of spread, but the scale on the y-axis is pretty, it's way lower than in a large city.
I
So
don't
then
know if the scatter is that much bigger. I think it's to do with the scale. The one you
Yeah.
showed before that was pretty tight. The scatter was between 800 and 1400. So look at the scale and see if you can put them all on the same scale, and you might be surprised that some of those that look like they have a giant scatter might just be because they fill the plot better.
Yeah.
Yeah.
And that's the sort of information that you can really tease out of, out of the information. Once you start to know what's happening on the ground, you've got a ground truth, what changes might be, what the differences are between different urban areas. So there could be that there's a lot of, there could be some quite big industrial processes going on in some areas, or a lot of outdoor sports, that, big floodlights. So there is a lot of testing of the data, but I'm not quite sure how you would go about that. I would be wanting to talk to the local districts, council people, and track when they started their LED changeovers. Look for new subdivisions or new commercial areas coming on stream, that sort of thing. So if we go back to the Queenstown Frankton example, within that 2012 to 2020 period, that whole Frankton development has taken place. And so, that has totally distorted anything that would show up in that area. That's the scale of change that I'd be looking for. I know that there's been a lot of discussion with the Queenstown Lakes District Council around lighting, and they do actually have a very good lighting policy or strategy, but it's the application of that strategy that they've fallen over with. So if you can put pressure on through conversation and through showing, information, data, it gives their staff a lot more ammunition to, employ compliance officers, that sort of approach.
Okay, thanks, Steve. Steve H, is there any questions coming to the chat?
No more questions into the chat.
Okay, well, in that case, we'll draw this session to a close, and once again thank both Heloise and Steve for their contributions. And and just a reminder that we'll have another session next week with 3 presentations, so hopefully you can tune in then. So good night from us.
Good night, Glenn. Good night. Thank you.
Bye.
Bye.